I just wanted to teach you about curve sketching today. So specifically, we're on the lesson Curve Sketching 2, which is where we build on our previous techniques for curve sketching, which I'll use the first derivative of the function. And we also now are going to start to include information that we can get from the second derivative of the function. So the new stuff here is this stuff called concavity, which is basically the function is going to be concave one way or another based on the sign of the second derivative. So concavity is kind of like the second order slope. So just recall that well, in the curve sketching that we've done up until now, we've been using the slope extensively, and we've been getting the slope information about our function f from its first derivative. So the first derivative tells us about the slope. The second derivative tells us about the concavity. So first of all, I need to define some terms about concavity, and then after I tell you a little bit about concavity, then I'm going to show you how we can use concavity information to sketch a function. Okay. So first of all, the definitions. So a function f is said to be concave up at a point x in its domain if and only if f double prime of x is greater than 0. So the second derivative being positive means that we are concave up. So what does that look like? If f is our function, and if we have a function that's concave up, it might look like this, like bowl-shaped, basically. Or it could be kind of bowl-shaped, but only like one-sided. So like if it looked like this, that would also be concave up. And it doesn't have to be positive. The function could be down here instead. That would still be concave up. Okay. And another thing that I just want to mention, although this isn't super important, but occasionally, and I don't think we do this in this class, but occasionally we refer to a function as convex instead of concave up. So I think that our textbook does not do that. We don't do that in this course, but that's the sort of terminology you might encounter in online resources if you end up using any online resources to help you solve these problems. So convex and concave up mean the same thing. Okay, so the second definition is concave down. And I just want to emphasize that the only points where our definition of concave up and concave down differ are here and here in the red. So a function is concave down if and only if its second derivative is negative. So concave up if the second derivative is positive, concave down if the second derivative is negative. So a function that's concave down might look something like this. Or it might look something like a one-sided version of that. So for example, it could look like this. And again, it doesn't have to be negative. It could be positive. This here looks a lot like a parabola, but it might not necessarily be a parabola just as long as it's got that general parabola shape. It could also be really narrow like this, or it could be really wide like this. Those curves would both be concave down. All right, so let me give you an example where we can determine where a function is concave up and concave down. So I'll just read this example out loud, and then I think you should probably pause the video and think about it based on those definitions, and then come back and watch me solve this example. So, okay, on what interval or intervals is the function f of x equals x squared concave up? And also, on what intervals is it concave down? So our function is f of x equals x squared, and we're being asked about concavity, right? We're asking where it's concave up and concave down. So we need to find the second derivative of this function. That's the first thing to do in this problem. Okay, so pause the video now, compute the second derivative, and see if you can determine the intervals where this thing is concave up and concave down. And if you've done that, if you do that successfully, then also try and determine what the graph of this function looks like. I think you know what this function looks like, but basically, graph the function and see if it conforms to the information that you find about where it's concave up and concave down. Okay, I will solve the problem in 3, 2, 1. All right. Now I'm going to solve the problem. Okay, so f of x is x squared. So we need to find its second derivative, right? How are we going to do that? Well, we got to find its first derivative first. So the first derivative of f of x equals x squared is 2x. The second derivative is 2. And one thing we notice is that 2 is always greater than 0. So the domain of our function is all real numbers. So the domain of this function f is all real numbers, so the interval from minus infinity to infinity. So the interval where this function is concave up is minus infinity to infinity, because this thing is always positive. The second derivative is always positive. Okay, and since the domain is minus infinity to infinity, and so is our interval where the function is concave up, that means it can't be concave down anywhere. So we can write that in a couple of ways. One is to use this empty set symbol, which is like a 0 with a slash drawn through it. This does not mean this does not mean 0. This set does not mean, or sorry, this symbol does not mean 0. It means the it's the empty set, which is to say a set that has no elements in it. It's not super important that you know that terminology. I just want you to know that this and the symbol 0 are two different things. 0 is a number. The empty set is a set. Anyway, so you can use the empty set symbol, and you can type that into WebAssign using the little CalcPad feature that it has. But you can also I think you can type in empty, and I would accept this as a written example, or a written answer on written assignments. You could write empty. You could write it in all caps. You don't have to write it in all caps. I think in WebAssign you probably have to write it in all caps, but for my purposes, it's fine if you don't write empty. You could also write the empty set. Sorry, it's fine if you don't write capitals. You could write it lowercase or. So what does this mean? What does this mean intuitively? What it means intuitively is that our function is concave down nowhere, right? Hang on, let me get myself a little additional space here. Oh, well, I guess I can't. Okay. So I could say that the function is concave down nowhere, or never concave down. The graph of our function, it looks like this. I think we know what the graph of f of x equals x squared looks like at this point. And I just wanted to point out that this looks exactly like one of these examples of a function that's concave up, right? Like these functions are concave up everywhere, so we'll just say for sure that they're concave up. And this f of x equals x squared here is concave up everywhere. And of course, concavity is mutually exclusive. So if it's concave up everywhere, that means it's concave down nowhere, etc. Okay. Okay, so that's our first example. So let's handle a little more of a complicated example here. So I've got the same question, and the only thing that I've changed is I've changed the function to be f of x equals the quantity x minus 1 to the fifth. So we want to determine the intervals where this thing is concave up and the intervals where it's concave down. So I will solve this problem in 3, 2, 1. All right, hopefully you took a whack at it. So I'm going to solve this guy now. So the first derivative of this, I'm going to use the chain rule. You could FOIL this thing out 5 times, which would be, it would give you a polynomial of degree 5. But it's easier to just use the chain rule and take in the derivative of this thing. So this would be, f prime of x would be 5 times x minus 1 to the fourth times x minus 1 prime by the chain rule, which would just be 5 times x minus 1 to the fourth, right? Because x minus 1 prime is just 1. So that's our first derivative. And then we're being asked about concavity, so really we're only interested in the second derivative of this guy. So what is that? So the second derivative of that would be the derivative of 5 times x minus 1 to the fourth power. So that would be 5 times 4 times x minus 1 to the third power times the derivative of x minus 1 again. Again, that's from the chain rule. This is a prime here, not a 1. So that would simplify to 20 times x minus 1 to the third power. Okay, so now we know that our second derivative of our function is 20 times x minus 1 to the third power. So what does that function look like? It looks like the following thing. We're just going to graph the second derivative here. So as you learned from pre-calculus, if you take a function like 20u cubed and you replace u with x minus k, that means you're going to shift the graph of 20u cubed to the right by k units. Okay. So in this case, we're going to be shifting the graph of 20x cubed to the right by 1 unit. So it's going to look like that. And then x cubed, we know, looks like this, right? So this would be 20x cubed. This would be our second derivative of our function. And this would be what its graph looks like. And this would be 1 here on the x-axis. So that's what the graph of our second derivative looks like. You could also, of course, solve for the zeros of this function and find what sign it takes, because we're really only interested in the sign of this thing. But regardless, we're interested in determining where our original function f is concave up and concave down, right? So remember that concave up is equivalent to checking when f double prime is greater than 0. And from this graph, or from checking numbers and checking where this function has its zeros, we can determine that this thing is concave up everywhere to the right of 1 on the x-axis. So that would be the interval from 1 to infinity. And where f is concave down would be where f double prime is less than 0, right? So in this case, f double prime is less than 0, means that the graph is in this part of the graph. And that's going to happen everywhere from minus infinity on up to 1. Okay, so now we've got a function which actually switches concavity. So our original function switches concavity. So does the derivative, actually, which is kind of a funny thing that's different about this problem. Okay, so now I'm going to use that information about concavity to sketch the graph of my function. So I know that from what we have done previously that f is equal to so I'll just write our function. F equals 0 if and only if x is equal to 1. So I can draw that point on our graph right away at x equals 1. And then the next thing I can do is I can look at the derivative of f to find out where it's increasing and decreasing. So f prime we decided was equal to 5 times x minus 1 to the fourth. I've gone off my color scheme here. Let me fix that. Okay, so f prime is 5 times x minus 1 to the fourth. So f prime equals 0 if and only if x equals 1. So I can draw a sign chart for all of my functions together. So I'll just do that. So it looks like the point where the only interesting thing happens is at x equals 1. And so I'll just draw the sign chart for f prime, and f double prime. So we know that f is x minus 1 to the fifth. So to the left of 1 there, since this is a fifth order root, using your curve sketching tools from pre-calculus, or just by checking a point in this interval from minus infinity to 1, you could see that, like, for example, f of 0 is equal to minus 1 to the fifth, which is equal to minus 1. So that's less than 0, and therefore f is negative on this interval, right? So all I did there was I checked a point 0, which is in this interval. And because f only changes values at x equals 1, it has to be negative on this whole interval. All right, so the next thing would be to check what happens when f is greater than 1. So I'll just check at f equals 2. And that gives me 2 minus 1 to the fifth, which would be 1 to the fifth, which is 1, which is greater than 0. So that means that f is positive on this interval. And what about f prime? Well, f prime is 5 times x minus 1 to the fourth, so f prime of 0 would be 5 times minus 1 to the fourth, which would be 5. That's greater than 0, so f prime is positive here. Okay, f prime of, f prime of, what am I looking at here? F prime of 2, if I want to see what sign f is taking on this, or f prime is taking on this side of 1, then f prime of 2 would be 5 times 2 minus 1 to the fourth power, which would be 5 times 1 to the fourth power, which is 5, which is again greater than 0. So f prime is positive over here. Oh, pardon me. And finally, f double prime. Let's see, the sign of f double prime. So f double prime of x would be, of 0 would be 20 times 0 minus 1 to the third power, which would be minus 20. That's less than 0, so we're negative here. And f double prime of 2 would be 20 times 2 minus 1 to the third power, which would be 20, so that's positive. So f double prime is positive. So we're concave up here, we're concave down here. We're negative to the left of 1, and we're positive to the right of 1. And we're increasing everywhere. So this tells me that my function x, or f of x, is going to look something like this. If I just include the information about increasing and where it's 0, then I get that f should look something like this. But the new information is this information about concavity. And so this tells me that f is concave down to the left of minus 1. So actually, instead of being a straight line here, I'm going to be concave down. So my function is going to look something more like this. And instead of a straight line here to the right of 1, I'm concave up to the right of 1. So my function is going to look something like this. And I think that if you plug this function into some graphing software, you can get a chart that looks indeed a lot like this. Okay, I will be back in a bit with an application to curve sketching where we're going to sketch a more complicated looking curve. Do this example. So this is the sort of a typical type of curve sketching problem that you might find on the homework. So you're given a function. It's kind of an ugly function. I don't really know how it behaves just by looking at it. And we want to sketch the function, basically. And to sketch the function, we're going to find a bunch of information about the function. We're going to find critical points, and we're going to find inflection points. And those critical points and inflection points are going to tell us stuff about the function, and then will result in a graph. So I'll give you a couple of seconds. Hopefully you can at least do this part of the problem on your own. And then we can also do these. So I just want to point out that this information here is all coming from the first derivative of our function. And this information down here is coming from the second derivative. So when the second derivative is 0, that's the inflection points. When the first derivative is 0, that's the critical points. And then the intervals of increase and decrease, etc., are taking place in between the critical points. The changes in concavity are taking place at inflection points. So I'll give you a couple seconds to compute this on your own, and then I'll go ahead and come back and solve this. Okay, so hopefully you paused the video to take a second to try this out on your own. So regardless of how far you got, I'm going to go ahead and do the full thing right now. So first of all, again, this information here comes from the first derivative, and this information here comes from the second derivative. So I need to compute those derivatives. So that's actually going to be how I start this problem. And it looks like I got some space there, so oops, right here. There we go. Here's my function. And from this function, it's pretty easy to compute the first and second derivative. It's just the power rule, because this function is just a polynomial. So I've got 3x squared minus 4x minus 7. And I can factor that, and actually I'm going to want to factor that, so I'll do that in a second. But before I do that, let's go ahead and compute the second derivative. So that's going to be 6x minus 4. Again, I can factor that. I can pull a 2 out, and that's going to be 2 times 3x minus 2. So that's going to mean that this thing is f double prime is 0 if and only if x is equal to 2 over 3. So that's going to end up being my inflection point, but I'll go over that in a second. First of all, I want to factor this first derivative. So how would I factor that? It's kind of ugly, so I'm going to use the quadratic formula. And let me just... So let's find the inflection points via the quadratic formula. So that's going to tell me that f prime is 0 if and only if x is equal to negative b. So that will be minus the quantity minus 4, plus or minus, the square root of b squared minus 4ac. So that would be 16 minus 4 times minus 7 times 4 times minus 7 times 3. Okay, all over 2a, so that would be 2 times 3, so that would be 6, and then those minus signs cancel there, so let me go ahead and find those roots. So that would be 4 plus or minus, let's see, x. Okay, so I can pull a 2 out of this thing, so that's going to give me 2 times 4 minus the quantity minus 7 times 3, all over 2 times 3, so I can cancel that, and that becomes a 2. So I've got 2 plus or minus, so I've got 1 over 3 times 2 plus or minus, let's see, that's going to be 21 plus 4, so it's going to be the square root of 25. So that's going to be 1 over 3 times 2 plus or minus 5. So it turns out that this is 7 over 3, and 2 minus 5 over 3, that would be minus 3 over 3. So your two solutions there are going to be 7 over 3 and minus 1. So therefore, our factored form of our first derivative is f prime of x equals 3 times x minus 7 over 3 times x plus 1, which is equivalent to saying that f prime is equal to 3x minus 7 times x plus 1. So anyway, that's the factored form of our derivative, and then therefore our critical points are these. So our critical points are minus 1 and 7 over 3. So now I need to determine when my function is increasing or decreasing. And the way I'm going to do that is I'm going to draw a little sign chart, just the standard way of doing that. So first of all, let me make another page here. I'm running out of space. All right, so now I need to make a sign chart. Pretty easily done. So my function only changes values at minus 1 and at 7 over 3. When x is less than minus 1, if I plug a value that's less than minus 1 into my function for f prime, I'm going to get a positive number, which is 3, times a number that's less than minus 1 going in here is going to give me a negative number. A number that's less than minus 1 going in here is going to give me a negative number. So positive times negative is positive. If you don't believe me, you can pick any point in this interval and check. So for example, at minus 10, f prime of minus 10 would be 3 times minus 10 minus 7 over 3 times minus 10 plus 1. So that would be 3 times some negative number times some negative number, because minus 10 plus 1 is a negative number. So those two negative numbers cancel each other and give me a positive answer. So that's why I'm positive over here. If I pick a number in between minus 1 and 7 over 3, like for example 0, that's going to make this first term positive, and the second term is going to be negative. So then I'll get positive, negative, positive, so this would be negative. And then if I pick a number that's greater than 7 over 3, like 10 for example, I'll get positive, positive, and positive, so this will be positive. You can also tell that by just checking one interval and looking at the multiplicities of these roots, and of course you could plug in some numbers. So you can also check by hand that, and I promise this is true, that f prime of 0 will end up being less than 0, and f prime of 10 will end up being greater than 0. So that's our sign chart for f prime. So that tells me that f prime is increasing. F is increasing where f prime is positive. So that's going to be on the interval from -infinity up to -1. So up to this point here. And then it's going to increase again from 7/3 to positive infinity. And you can write a set of intervals like this with a comma in between them or with the little union symbol. I kind of prefer the union symbol, so you probably see me write it like that most of the time, but a comma is fine. All right, and we want to also find the intervals where f is decreasing, so that's going to be where f prime is less than 0. So f prime less than 0. So when is f prime less than 0? Only between -1 and 7/3, right? So -1 to 7/3. And okay, local minima, that's when the function is going to change from decreasing to increasing. If my function is decreasing and then it starts increasing, that means that I just passed a valley in my function, so that's going to be a local minimum. So I'm decreasing on this interval, and then I switch to increasing here. So I'm going to have a local min at 7/3. Local maxima, it looks like there's one here. So if my function is increasing and then it starts decreasing, that's going to be local maximum. So that's going to be max. So that would be x equals -1 is the local max. So now I know some information about my function. And so I'm ready to graph it already, but I haven't looked at the second derivative yet. So just from this, I can get a graph as the function, but the second derivative will help me make that graph a little bit more accurate, basically. So yeah, why don't I graph this thing? So okay, what do I know? I've got critical points at -1 and 7/3. In fact, I have a local minimum at 7/3 and a local maximum at -1. So I've got a minimum at, I've got a local max at -1, and I've got a local min at 7/3. Sorry, that should be a little further out on that axis. Rather, I should put this one further in. All right, so I said max at 1, so my function looks like this at 1, and my function is then going to go down until it hits 7/3 and then go back up again. So that's my basic idea of my function x so far. Yeah, I should label this axis. This is the x-axis. Concavity is going to tell me some additional information that I can put on this graph. So I'm actually going to put the concavity stuff below this graph to kind of clear it up. So this is my graph based on the first derivative. Okay, so that's what I know based on f prime of x. So the next thing I would like to do is interpret this this formula that I've got for f double prime and use that to alter my graph accordingly. So I've got an inflection point here when f double prime is 0, right? So my inflection points are when my function is not defined or when its second derivative is 0. So f double prime is 0. That's equivalent to saying 2 times 3x minus 2 equals 0. So I can divide both sides by 2, and I just get that over 2 equals 0/2. So then 3x minus 2 is equal to 0. So 3x is 2. So x is equal to 2/3. Okay, so that's my inflection point. And then if I plug that back in, do I get 0? Yes, I do. Okay. So now I want to look at concavity, right? So to find concavity, I'm going to look at a sign chart of my function. So here's my function f double prime. and the only inflection point is at 2/3. It's possible, of course, to have a function that has more than one inflection point, at which point you'd have to draw more points on this chart, as usual. But in this case, the only inflection point is at 2/3. So I just want to check what is the sign of f on this interval, and what is the sign of f on this interval, right? And that's going to tell me where it's concave up and concave down. So to find the sign of f on this interval, I'll just plug in any point in that interval. So I'll plug in x equals 0. That would be a good one. So f double prime of 0 is, well, where's my f double prime? It's this. Okay, so it's 2 times 3 times 0 minus 2. So that would be 2 times 0 minus 2, which would be 2 times minus 2, so that's minus 4. It's less than 0. So that means that my function is negative here. It's negative on this whole interval. Specifically, f double prime is less than 0 on the interval from minus infinity to 2/3. And that tells me that f is concave down, by definition of concave down, on that same interval. Minus infinity to 2/3. Okay, so that's one of these answers already. So minus infinity to 2/3. And let's do the next one, the next interval. I just need to pick a random point in this interval. I could pick 1, for example. I could pick 2. I could pick 100. And I'm just going to go ahead and do 100 here just to demonstrate that any point will work. So f double prime of 100 will be 2 times 3 times 100 minus 2. And the exact number isn't too important. All I really care about is the sign. So this is positive, and this is positive. And if I take a positive number and I multiply it by another positive number, I get a positive number, right? So this thing is greater than 0, so I'm positive on this interval. Okay. So what does that tell me? That tells me that f double prime is greater than 0 on the interval from 2/3 all the way to positive infinity. And that tells me that f is concave up on that same interval, 2/3 to infinity. And let me just copy this down. Okay, so we have an inflection point at 2/3, and we found where it's concave down, and now we just found where it's concave up. So 2/3 to infinity. Now, it's possible, if your function is kind of funny, that you might have actually ended up with a plus here and a plus here. And if that happened, then your function would be concave up everywhere from minus infinity. You would move this into the concave up category. So you get the union of those two intervals. Similarly, if you got, Similarly, if you got a negative sign here, then we would have concluded that f was concave down, not up, and then we would move this this interval here to the concave down category, and we would take the union. So it's possible for funny stuff like that to happen, but in this case, our function behaves kind of normally. So how does that inform our graph? So let me just copy down the graph as it was based on the first derivative. So our working graph looked like this. And now we've got a little bit more information. So we've got 7/3, and then we've got a new point, which is our inflection point at 2/3. And okay, so our graph is changing from concave up to concave down at 2/3. Rather, the other way. It's changing from concave down to concave up at 2/3. So instead of my function being straight lines like this, what I've actually got is something that looks concave down happening between minus infinity and 2/3. So, right, 2/3 and minus infinity is concave down. So in that case, my function looks something more like that. And then at 2 over 3, my function is going to change. That's the inflection point, and it's going to become concave up. So instead of being straight lines, it looks more like this. So that's our graph based on our second derivative. Okay, I think that should cover it. I want to make one note, which is that in a lot of problems, you start with, it doesn't give you the exact function. Instead, it just gives you the first derivative directly. And so if you're in that sort of situation, you can kind of proceed the same way. You just won't be able to ever compute f of x. So I didn't actually do a super accurate plot here anyway, because I know that you guys have a lot of problems like that. So if you knew f of x, then you could hypothetically find exactly where f is crossing the x-axis. You could find exactly its value at these important points. And you can make your graph a lot more accurate. This graph probably isn't very accurate in terms of like the actual size of f. It's just accurate in terms of where it's increasing and decreasing. So if you're not given f, then you won't be able to do that information anyway, so you can proceed exactly as I have here. You start with the first derivative, you find all the first derivative stuff, you end up with a graph like this, and then from the first derivative, you can take the derivative of that again to get the second derivative, and from the second derivative, where did it go? From the second derivative, you can proceed according to this, according to the steps I've outlined here. And you will ultimately end up with some intervals of concavity, and that can inform your plot accordingly. Okay, I hope that helps. Talk to you later.